Hello again. I'm Gary Millette. I'm going to be your guide through topic number 4, electromagnetic propagation and transmission lines. This is a very short presentation that'll just hit the real important topics, and let's get started. So, to appreciate why certain radio frequencies are now used for specific services requires one to examine how electromagnetic, or EM, energy propagates. As indicated earlier in another wireless presentation, the early work of the wireless pioneers was performed at low frequencies with crude transmitters based on electric spark gap or rotating alternator/generator technology. This nearly exclusive use of low frequencies changed when vacuum tubes came into use, as mentioned earlier. So there was a march towards higher frequencies. However, one should be aware that it has been a century-long journey from the use of frequencies in the single megahertz range to the use of frequencies in the upper millimeter wave regime for practical applications. During that time, as pointed out in the presentation about active devices, the vacuum tube has been replaced by solid-state devices, and their physical architectures are quite unlike that of the original transistors known as point contact and bipolar junction devices. Let's start our discussion of electromagnetic propagation by looking at the electromagnetic spectrum. So here's a picture of the electromagnetic spectrum. I'll talk about it a little bit, but we're going to talk about it more as we go along. If you take a look, it starts at 30 hertz and goes by decades. The next 300 hertz, 3 kilohertz, 30 kilohertz, 300 kilohertz, 3 megahertz. That's in the top portion of this. And in the very top, you see things like power frequencies, audio signals, maritime mobile radio navigation, AM broadcasting. So basically, it's telling you what services are there. Above the 30 hertz, you see 10 megameters. Above, say, 3 megahertz, you see 100 meters. So what happens is it's showing the wavelength, and wavelength is given by the little equation at the far end by the arrow there, lambda over f, lambda over frequency. So, well, I should say that the lambda is the wavelength, which is on the top scale, and frequency is the frequency on the bottom scale. Another thing is you might notice ELF, between 30 hertz and 300 hertz. That stands for extremely low frequencies. VF is voice frequencies. VLF is very low frequency. LF, low frequency. MF is medium frequency. So those are the frequencies we started with. And as time's gone on, we've moved to the bottom little diagram there. And you might notice that the first designation is 100 meters, then 10 meters, 1 meter, 10 centimeters, 1 centimeter, 1 millimeter, 100 micrometers. 100 meters is 3 megahertz. 100 micrometers is 3 terahertz. So we go from 3 to 30 megahertz is high frequency. 30 to 300 is VHF. 300 to 3 gigahertz, ultra high frequency. 3 gigahertz to 30 gigahertz, super high frequency. 30 gigahertz to 300 gigahertz, extremely high frequency. We don't have a designation yet really for 300 gigahertz to 3 terahertz. We might call that infrared, actually. Up above, we see shortwave broadcasting for the high frequencies. For VHF, we have FM, TV, public service. For UHF, TV, cellular, wireless LANs. Super high frequency, satellite TV, radar, LMDS, which is a service which is really a local microwave distribution service, which has really gone away at this point in time. 30 gigahertz to 300 gigahertz, millimeter waves, radar, again LMDS, 300 gigahertz to 3 terahertz, sub-millimeter waves, medical. So again, we really have how many decades? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 decades worth of frequency spectrum that's useful to us at this point in time. And again, if things look chronological there, they certainly are. You know, we started in the top portion of that diagram and have moved along as we've gone along with innovations and new technology. moving past 3 megahertz to the shortwave frequencies and then higher and higher. But it has been a long battle, again, close to 100 years. So if you look at the previous slide, again, there are letter designations and brief descriptions of applications or services associated with a particular frequency range. So I'm going to skip over the slide. We already talked about this. Over time, the different decades of electromagnetic wavelength or frequency have been given acronyms to identify them. We talked about this also. They became available for use due to the maturing of electronic devices or because of other technological innovations. Wireless started in the VLF frequency range, the very low frequency range, but moved to the MF or medium frequency range by the time widespread AM broadcasting started. FM broadcasting and TV moved the technology into the VHF and UHF regions. Wi-Fi started in the UHF band. So here's a equation for wavelengths, how you can figure it out. And wavelength is equal to C, the speed of light, divided by F, the frequency in hertz. And if you look back at that chart, a frequency of 300 kilohertz had a wavelength of 1 kilometer. A frequency of 300 megahertz is a wavelength of 1 meter. And a frequency of 300 gigahertz, a wavelength of 1 millimeter. The wavelengths are in decades on the slide. We mentioned that also. So as a general approximation, the length of a practical wireless antenna should be an appreciable fraction or the same order size as the signal wavelength. So you might recall the early wireless radio systems at very low frequency and low frequencies. They required extremely tall vertical antennas, which were really impractical. However, consider an antenna for the millimeter wave frequency band. It can be extremely small, which opens up many possible designs, including vast arrays on ICs for frequencies in the millimeter and sub-millimeter range. Other electromagnetic wave properties. So far, the only property we've looked at is the wavelength, and is indeed an important property. Another property is polarization. What this is the orientation of the electric field of an electromagnetic wave. The magnetic field of the electromagnetic wave is perpendicular to the electric field, and both fields are perpendicular to the direction of propagation. You might want to do a Google search on electromagnetic wave applets to see animations of propagating electromagnetic waves. Our next slide will show you a model. So here's an electromagnetic wave. The blue is the electric field, the red is the magnetic field, and notice the propagation direction perpendicular to both the electric and magnetic fields. Notice the electric fields and magnetic fields are sine waves, and there's a designation of a wavelength there from the tops of two magnetic field peaks. So we also call this a transverse wave or TE mode wave. There are other modes of operation. The wavelength of an electromagnetic wave is equal to the distance the wave can travel away from its source, which would be an antenna, at the speed of light during the time that the signal has gone through one cycle. So the wavelength shown there, the designation is that the tip furthest to the right has traveled that distance in the time it's gone through one cycle. We're back to the same point on the wave, which is a cycle. The polarization of electromagnetic waves is an important property when it comes to antennas. A vertical antenna emits a vertically polarized electromagnetic wave, whereas a horizontal antenna emits a horizontally polarized electromagnetic wave. To receive a signal effectively, an antenna must have the same polarization as the electromagnetic wave. Two antennas at right angles to one another will not interact. Electromagnetic waves all share the same propagation properties. And due to our life experience of having eyesight, we are aware of most of these properties since light is also an electromagnetic wave. The properties are reflection, refraction, diffraction, interference, absorption, and the Doppler effect. In the interest of time, only short descriptions of these effects will be given in the context of wireless communications. Just like light reflects off of a shiny surface, electromagnetic waves reflect off the surface/interface between different transmission mediums, i.e. materials. The amount of reflection depends upon the properties of the new medium, that the electromagnetic wave encounters. For an example, an electromagnetic wave passes through glass fairly easily, but reflects off of a good conductor, 100% reflection. Materials with properties in between these two would give rise to a partial reflection between 5% to almost 100%. It all depends upon the material. As an electromagnetic wave passes from one medium to another, it changes speed depending upon the material's dielectric constant. This effect gives rise to the refraction or bending of the electromagnetic wave when it enters a new material at an angle. Snell's law predicts the resulting angle of propagation of the wave in the new material. However, there are some special angles and polarizations that yield special cases like total internal reflection. This is the property used to construct early fiber optic cables. Electromagnetic wave propagation diffraction. This electromagnetic wave property is not easy to observe with light unless one uses a diffraction grating, but there are many instances of it for electromagnetic wave propagation. This property allows electromagnetic waves to propagate around corners, so to speak. What is meant by this is that diffracted electromagnetic waves will weakly illuminate the shadow area behind an object. This is not a bad thing when one desires cell phone service, but it does have an adverse effect on signal strength and gives rise to signal fading effects. What about interference? Interference occurs to electromagnetic waves when a signal reaches a particular point after taking several to many different routes to get to that point. That would be LOS, which is line of sight, and NLOS, non-line of sight paths. This effect can happen due to reflections, refraction, and diffraction. Since the signals take different amounts of time to travel the different paths to the destination point, they have different phases and will therefore add vectorially once there. The effect is known as either constructive or destructive wave interference. So here's a slide which shows a multipath outdoor interference diagram. The transmitter is over in the far left, and we have all these different things like buildings, diffraction, line of sight propagation, ground reflections, and they all arrive at a point on the top of that old-fashioned station wagon. So the figure shows how signal interference might occur due to multipath environment that can exist due to the surroundings and various electromagnetic propagation effects. Note the line of sight signal path directly, and that would be the fastest way the signal got there. However, other signals due to different propagation times might be 180 degrees out of phase with the line of sight signal or vice versa. Also inside you can have this multiple path indoor interference. So this kind of shows a building with the walls and so forth. This figure shows how an indoor environment can create a multipath interference situation, just like the outdoor case shown on the previous slide. Various metal objects in the rooms can cause signal reflections. And there's an antenna on that computer sitting in the top right-hand side there, and notice how the wireless access point signals have gotten to it by going through different paths. And different length paths mean different phase angles, and again, you'll have vector addition at the destination. If the propagation effects causing the interference vary with time, due to motion or for other reasons, then fading occurs to the signal strength at the receiver. In the prior slide, that wouldn't be a case, but if you think about the old station wagon in the slide before that, as it's driving along, all the paths would change. So you could get fading. In the wireless communications field, this type of usually rapid fading is known as Rayleigh fading. Various forms of digital signal transmission like OFDMA can be used to mitigate this effect, which is usually a function of both time and frequency. Another effect that can occur is signal dispersion due to different propagation speeds. This effect tends to lower the possible data transmission speed. And you might be aware of dispersion from thunder. If a thunderstorm is right next to where you are, there's a crack of thunder, whereas if it's far away, the sound waves disperse and you get rumbling effects. How about electromagnetic wave absorption? So electromagnetic waves can be absorbed as they propagate through a lossy medium. We all know that our cell phones usually work inside of a building, but what if one is in a sub-basement or gets into an elevator, which is basically a metal box? Different materials have different loss factors for different frequencies or wavelengths. A 100 megahertz signal in the FM band seems to have no trouble penetrating the brick or cement walls of a building, but that would not be the case for a frequency above 15 gigahertz. Electromagnetic waves can be absorbed by the Earth's atmosphere or by precipitation falling through the atmosphere. This first effect does not typically influence frequencies below about 10 gigahertz. However, above 10 gigahertz, there are frequencies that are very lossy for electromagnetic waves. One of these particular frequencies is roughly 60 gigahertz, which is a new band opened by the FCC for the IEEE wireless technologies. This is not a coincidence. This atmospheric absorption effect will let lands at the frequency coexist with minimal spacing. How about the Doppler effect? Most of us are aware of the Doppler effect, or at least know that it is a principle used by law enforcement to check our car speed. If a source of a signal is either moving towards the receiver or away from the receiver, the source frequency appears to shift up or down, respectively, to an observer. There is a well-defined equation that relates the frequency shift to the relative speed of the source and the receiver. This frequency is easily detected by a simple radar system. Doppler radar is a term used by many for weather radar systems. However, the principle of operation of these systems has little to do with the Doppler effect. The amount of radar signal reflection is the indication of the location and the amount/rate of precipitation that eventually undergoes signal processing and colorization before being shown on a visual display. Certainly, you can use the Doppler effect to see how fast things are moving, like a weather system. Also, weather conditions can cause short-term, hours in duration, for instance, effects like super-refraction of signals in the atmosphere. If we cook food in a microwave oven, and yet we can look into the oven and see what's going on, how is this possible? Why isn't this dangerous? It is due to another propagation effect. Electromagnetic waves will not enter into a space/aperture/hole in a conducting plane that is not at least a half of a wavelength in one dimension. Examine the metal screening on your microwave door. The microwave oven operates at a frequency of 2.45 gigahertz with a wavelength of about 12 centimeters or about 5 inches. Most viewing screens or windows have a much closer spacing of the holes or openings in the screen. Thus, the waves will not propagate through, and you're safe to look into a microwave oven as it's operational. Before we leave this topic of electromagnetic wave propagation, let's discuss how electromagnetic waves propagate on the surface of the Earth. That's known as terrestrial propagation. Low frequencies, long wavelengths, signals below approximately 2 megahertz or 150 meters in length, travel along the Earth's surface in a mode called ground waves, which is typical for AM broadcasting stations. The antennas for these signals must be vertically oriented. Otherwise, the electromagnetic wave's electric field would be absorbed by the ground's conductivity and die out very quickly. What about medium frequencies? So medium frequency signals between approximately 2 and 30 megahertz propagate by interacting with the ionospheric layers in a mode known as space waves. These signals may be transmitted with horizontal polarization. It's typical of shortwave radio transmission. Once transmitted, they can reflect off the various ionospheric layers that exist in the Earth's upper atmosphere. It is possible for these signals to reflect back and forth from the Earth's surface and these layers so that the signals go completely around the Earth. This effect is sometimes known as skip or hop. It is possible for low-power signals to go all the way around the world. There have been reports of people talking from the United States to, say, China on 5 watts of RF power. High frequency or short wavelength electromagnetic waves, that is above approximately 30 megahertz or 10 meters, travel in direct line of sight, LOS paths, or rays only limited in propagation distance by the Earth's curvature. We all know the story of the fact that the Earth, if you watch a boat leave a port, eventually it disappears because of the Earth's curvature. Over-the-air broadcasting services like TV or FM are limited by their line of sight or radio horizon distance. This last fact is the reason for FM and TV transmitting antennas being located on top of tall buildings, towers, or towers on mountains. These locations increase their effective transmitting range and, of course, hence their the more people can view the signal or hear it. So all the wireless networking technologies or transmission methods utilizing frequencies in the VHF and UHF bands or higher frequency bands, like microwaves and millimeter waves. Thus, the electromagnetic waves travel in line-of-sight mode or straight lines unless they encounter a new medium that causes various propagation effects to come into play. As I already pointed out, these various propagation effects can cause interference by providing non-line-of-sight paths from the source to the destination that cause disruptive effects to receive signal power and hence data transfer. So just to repeat, all of our wireless networking technologies work on the VHF, UHF bands and higher, so they'll all be line-of-sight type of operations. Before we leave this topic, we should really take a look at the topic of transmission lines and how electromagnetic waves propagate on these structures. So a transmission line is used to direct RF electromagnetic energy from point to point efficiently. And there's a lot of lore about this. We're going to only cover it in a few slides, but nevertheless, there are different types of transmission lines depending upon the application, conductor-based and non-conductor-based. For instance, for data delivery by twisted pair cable, that is pairs of wires, category N is used. So we have category 5, category 6, category 7, for instance. For wireless RF systems, coaxial cable is a transmission line of choice. So coaxial cable, or coax, is constructed as concentric conductors, has good noise immunity, and has standard connectors to interface the cable run to and from equipment. Electromagnetic waves suffer the same propagation effects on transmission lines as suffered by propagating through air or space. The cables have loss, so the signal is attenuating going through the cable. So here's a picture of some coaxial cables. They show many different forms of coaxial cables, can take on different applications. Shown on the left is but a few of standard coaxial connectors that are available for use with available coaxial cables. And you might notice that some of those cables are flexible, others are covered by black plastic and so forth. There's all kinds of different connectors on the ends. The picture on the right shows the newest popular connectors for wireless equipment, SMA connectors. So, where do we use transmission lines? So, due to their inherent signal attenuation, the shortest cable run should be used if a transmission line must be used in the wireless system. If the transmission line becomes crimped or otherwise damaged, the signal energy will be reflected from the damaged area, much like a sound echo. External antennas, if needed for wireless data transmission systems like WiMAX, must use the proper type of coaxial cable transmission line. I think we mentioned this before. For wireless RF systems, a 50 ohm coaxial cable transmission line is the industry standard. Most LAN and PAN equipment is small in size and self-contained. Therefore, the wireless antenna systems are usually connected directly to the LAN device or on the printed circuit board of the PAN device. These devices typically use transmission lines that are an integral part of a printed circuit board. These transmission lines are known as microstrip. They're flat metal wires on printed circuit boards. Again, electromagnetic wave energy propagates on these transmission lines just like any other type of conductor-based transmission line. Recently, if long distances must be traversed, manufacturers of wireless data transmission systems have begun to send RF signals over fiber optic cables. This technique allows equipment to be located some distance away from an antenna or at the bottom of a tower, and the low loss of the fiber optic cable does not degrade the system. This technique can be used for both cellular and the IEEE wireless data technologies. So as new frequencies in the millimeter wave frequency bands, 60, 70, 80, 90 gigahertz, are used for wireless data transmission systems, it is crucial that antenna systems be an integral part of the wireless networking device, maybe even part of an IC chip. At these frequencies, even inches of transmission lines contribute large losses. Gone are the metal waveguides of a bygone era. Microstrip or dielectric and coplanar waveguides are the structures used to implement transmission lines today at millimeter wave wavelengths. So we summarize this. For any wireless networking technology, there is a transmitter-receiver device that is connected to the internet and can talk to your device to provide internet connectivity. The electromagnetic signals from this device will be affected by the surrounding environment. The effect of the surrounding environment is frequency dependent, and therefore external or high gain directional antennas may have to be used and be connected via standard transmission line.